Welcome to Darshil Shah, who is assistant professor at the University of Cambridge in the United Kingdom. And he will make a presentation about designing next generation small wind turbines for the plant-based materials, engineered timber towers and flax or hemp, Biocomposites composites blades. Are you ready, Darshil?
Yes, I am. I'm just about to share my screen. So
yes, it's coming now, I can see.
Fabulous.
Probably you can put it up for full screen.
Yep.
Thank you very much. It's good and clear. Thank you.
Fabulous. Thank you. Thank you for having me. And I'm looking forward to your comments and thoughts as well following the presentation. And feel free to interject me if you do have any questions in the middle of the presentation as well. So yes, I'll be presenting on some of the work that we've been doing on trying to produce wind turbines, small wind turbines with natural materials. I'm based at the Center for Natural Material Innovation at the University of Cambridge. We are located at the Department of Architecture, but we work across different departments at the university. And we use a multi-scale approach across the length scales, trying to think about the building blocks of natural materials. So for example, in this case, you will be able to see the cell wall polymers in timber or plant fibers, and how we may be able to modify these, for example, through genetic modification of plants. So with biochemists and plant scientists, we work with Arabidopsis, which is the mouse of the plant world, to try and modify very tiny functional groups and how that influences the molecular makeup and arrangement of these polymers and therefore the emerging properties of the eventual material as well. And then at the tissue scale, we work with chemists and fluid mechanicists to try and modify timber to make it more durable, for example. So we work with both archaeological materials. So the Mary Rose ship, for example, which is a waterlogged 16th century ship. If you bring that out of the water, what happens to the timber because of the drying and the warping and the removal of the water, and how you can stabilize it, but also at the building scale, how to make wood or plant-based materials much more durable in the presence of fire, in the presence of moisture, for example, by impregnating them with polymers or locally stiffening them. And then we also work at the material scale, trying to understand what happens if you're making cross-laminated timber, which is panels that are several meters long, also glue lamp beams, and we test quite large specimens, half a meter or a meter in dimension, and we need 5 meganewton testing machines to test these, very much like a small wind turbine blade actually. And then we work with architects and engineers to try and design towers, so buildings that are 300-meter tall. We have developed some of these concept designs, but we also work at the more reasonable scale of developing schools that are 2 or 3-story tall, but on a larger floor area. There are a couple of YouTube videos if you're interested in hearing more about that sort of architectural research. So here are a couple of images showing you the scales we work at. Here we are testing genetically modified plant stems, which are just a millimeter in dimension. We also work at the nanoscale, trying to use nano indentation to understand cell wall properties. But here you can see a few meters in length glue lamp beam that we are testing on a 5 meganewton testing machine, quite an old machine, this one. Timber has become quite an emerging material and advanced material because of its engineered nature nowadays, particularly with the advent of cross-laminated timber and glue-laminated timber. So for example, in Norway, we have quite a few tall timber buildings. This is the Mjøstarnet building, which is 18 stories tall, 85 meters, produced using LVL, laminated veneer lumber, which I have some specimens over here. You can see very thin veneers of beech wood that are compressed all in the same direction to produce this sort of material. And the advantage is because it's a highly digitized process, you're getting rid of knots, for example, and weak points. And this product would be 4 to 7 times higher in strength than just sawn timber. And that is what enables to produce such tall structures. On the right of this slide, you can see the tallest tree in the world, Hyperion, which is 115 meters tall. So we still haven't made timber buildings as tall as the tallest tree in the world. So a bit of way to go, but that is the aspiration, at least. And I'm sure you have heard of Modvian, who are now looking to develop timber towers that are up to 140 meters tall. So here is a slide where quite a few years ago, when I was a PhD student at the University of Nottingham in the wind energy group, we were trying to use natural materials and automated manufacturing processes for the fabrication of small wind turbine blades. So using film, reusable silicon molds for single shot infusion molded 3 to 5 meter long turbine blades for 11 to 25 kilowatt machines. A picture over here, you can see the Ratcliffe on Soar power station, which is coal-fired, and the wind turbine that we had installed as an experimental machine on site. But one of the key ideas that I wanted to demonstrate over here is you have this disparity between our energy uses, but also to bear in mind that there is still possibilities of making renewable energy even more sustainable by trying to produce the turbine from more natural materials, because energy is material and material is energy. And a lot of it is related to the tower itself, which is typically made from steel. So I think most towers are made from steel, and the blades are typically made from fiberglass, but also carbon fiber reinforced plastics. In proportion, usually the tower represents around 60 to 70% of the weight of the turbine, and the blades are around 10 to 15% of the weight of a turbine. Lots of companies now, because of initiatives such as meeting carbon neutrality and zero waste. So Vestas has its 2035 and 2050 policy of, or aspiration of being carbon neutral without being carbon neutral, as well as aspiration of being zero waste. So you've come across some of these pictures of landfilled wind turbine blades at their end of life. And given the plastic ocean challenges that we are currently facing, we want to avoid a situation where we are having to dispose of composites, which are notoriously difficult to recycle through landfilling processes. Thermoplastics are becoming more and more possible, and this is particularly the case with smaller wind turbine blades, because then you can recycle the composite material a bit more readily in comparison to thermoset-based composites. Incineration may also be an option, particularly if the fibers are not inorganic, so like glass-based. It's just more economically viable to either landfill them or to mechanically degrade them and then use them as fillers in concrete, for instance. But the vision that we have set is to try and produce the towers from timber and the blades from more bio-based materials as well. So here you can see a schematic from a paper that we put together quite recently, in which the aspiration is that if the blades were made from textiles that were plant fiber based, and these plant fibers would have undergone processes of spinning, sliver production, so roving and yarn production, as well as fiber extraction from fibers that we grow from agriculture. So here we have hemp, but there are a load of other varieties of plant fibers that are available to us. I recognize when I think it was Mike that was speaking, behind him was a painting of bamboo. So bamboo is another material that we work with as well. So alongside timber, bamboo towers may be a possibility based on the local availability of materials. So here are a couple of YouTube videos. I might try and turn the music off. So two different worlds over here. On the top left, you are seeing Wicken Smock Mill, which is a smock mill produced after tower mills quite early on. And these were built for corn production, but also historically in Cambridge, where I am based, a lot of this used to be fenlands and it was covered in water, and we took the technology from Netherlands and Denmark to try and remove water and peat, and that's what some of these mills were used to do. In this case, the towers were typically made from timber and the blades were also made from wood. Here at the bottom right, you see Modvion, who very recently in Sweden, and I think they've just been bought over by Vestas, have produced a 30-meter prototype tower made from timber. Quite different timbers. In this case, we have traditional sawn timber. Over here, Modvion is using glue laminated timber in a modular fashion and erecting it to quite large spans. Something interesting that you might notice is that when you are designing with natural materials, you may have to detail differently. So in the case of both the, if I try and get to, if I come here, you can see that the base of the wind turbine tower for the Modvion is steel, and the base for the Wicken Smock Mill is made from masonry. And typically, because timber doesn't do that well with moisture, you want to keep it away from the ground. And that's often done with houses in the UK and around the world as well, because of the end grain moisture absorption. So that's a design detail that you have to incorporate and think about when you are designing with natural materials. But it's just to demonstrate that if 30-meter wind turbine towers are possible, and we have historically built smock mills with timber as well, small timber towers shouldn't be very difficult to construct and fabricate. This is also supported by the fact that increasingly the timber sector is very digitized. Forests are sustainably managed, and using LiDAR technology, you can see how many trees have been growing, what their typical heights are, and using tree scanning technology, measure the amount of wood in the tree, where the knots are likely to be, and how parametrically in a sawmill you may want to cut it so that you're getting the most amount of timber, or at least the highest grades of timber. And then also fabricating these into complex engineered materials with much more stable and reliable properties, such as laminated veneer lumber, glue laminated timber, and cross-laminated timber. And then finally using robotic and automated assembly construction to produce quite intricate components that are curved. And with Modvion, for example, you saw some of these curved timber tower modules as well. And with modular construction, how these can be assembled together quite cleverly using either timber connections. So you may have come across specific dowels that are made from timber, but also using steel metallic connections. One of the advantages of natural materials is their lightweight, particularly in comparison to their stiffness and strength. And in the case of wind turbine applications, both the tower and the blade are facing quite a lot of cantilevering loads, so it's bending loads, and therefore stiffness to the power of A third over row is an important material performance index that you would want to optimize. And in that respect, timbers can perform favorably even in comparison to steel. So that's just an aspiration, and we are working on a project to develop a 7-meter engineered timber tower to replace an existing 1 kilowatt tower that we have on site. Moving on to biocomposites, I wanted to showcase some historic precedents to you as well, in case you're not familiar with them. So you may have come across Henry Ford's green car, which had composite panels that were made from cellulosic fibers, primarily hemp and straw, and also reinforcing a soybean oil-based phenolic matrix. And these were to replace steel in the 1940s. So this is just before when oil became suddenly really cheap and plastics became a bit more common and glass fiber took off after that. Also, soon after, hemp was banned for growing in the US as well. So that took a shock to the industry. Similarly, in the UK, very close to here in Duxford, Cambridge, they were developing Gordon Aerolite, which is a flax phenolic composite for constructing Spitfire fuselages as a replacement for aluminum. And again here, the specific strength and stiffness of the material was critical. There are quite a few applications around the world. Recently we have come across Trabant, which in Germany was used for cotton phenolic composite parts for automobiles. And very recently, a couple of months ago, Cycomin and Green Boats have come together to fabricate one of the world's first natural fiber nacelle cases for offshore wind turbines. And I think this is a 7-meter nacelle case using a bio-based epoxy and natural fibers in their nacelles. So it's, I think, happening, especially for larger turbines. So smaller wind turbines, we hope, would be definitely possible. Currently, plant fiber composites are almost exclusively used in automotive interior components, but there are one-off products that have been developed for the sporting sector and for consumer goods, as you can see over here. But I said mostly these are in automobile applications. If you look at the composite sector in Europe, in the EU, the biocomposite sector is significantly larger than the carbon fiber composite sector. I think it's, in terms of volume, it's 7 times larger or so. And yet we hear more about carbon fiber composites than bio-based composites. Nevertheless, in terms of the applications of the fiber, for flax fibers, which are one of the strongest of the natural fibers, only 3% of the overall output in France, at least, which is one of the largest producers of flax in Europe and in the world, goes into technical applications. A majority of it still goes into fashion, decoration, and household items. So how do you design a biocomposite blade? So that will be the focus of the next 5-10 minutes, I think. So blades, we all know, are a model structural component. They have a design life of 20 to 30 years. They have quite large fatigue loads, especially because they are rotating at 200 RPM or so, or even faster. And both static loads and fatigue loads are important for them, particularly considering extreme wind load conditions based on the IEC 61400 standard. So a model product to explore. So what we were trying to do was design biocomposite blades for an 11 kilowatt wind turbine, horizontal axis, 3.5 meter blades. And we thought of a conventional blade construction in which we have triaxial materials on the outer skins. We have a unidirectional spar and then a polyurethane foam in the middle, produced using a single shot infusion process, a fiber volume fraction of 32 to 38% or so based on the length of the blade. Now you can tailor the material properties of your composite using either changing the fiber and the matrix. You can change the architecture of the fiber, so the orientation. You can also change the composition. So we looked at a variety of different plant fibers, and loads are available to us. Based on these, we eventually did a material selection process to try and identify which bast fibers will have best strength and stiffness. And it turns out bast fibers, which are in the stem of a plant, such as flax, hemp, and jute, are the most suitable, particularly in stiffness and strength dominated applications. So that's what we went ahead with. Here are some pictures of hemp fibers, or hemp that is grown in the UK, that we have been using more recently. And just to give you a flavor of how hemp varieties and flax plant fiber varieties have evolved over centuries or decades even, here you can see the stalk of hemp in 1960, and in 2017, you can see the amount of fiber yield that has increased, and also the impact of the variety and the region of growth from either Italy, France, Poland, or UK, and the climatic conditions on the properties of the fibers that you can get. So the selection of the fiber is quite critical and something to bear in mind. But eventually flax, hemp, jute are the key ones we take forward. We also wanted to optimize the fiber content, and we realized that there was a very narrow window of fiber manufacture volume fraction that we could use, and this was around 30 to 45%. It's really hard to get higher fiber volume fractions because of the lofty nature and the discrete lengths of plant fibers. Something else to bear in mind with plant fibers during the design is the nonlinear stress strain response of plant fibers at each length scale. So at the fiber length scale, as well as at the yarn and composite scale, and orienting the fiber to the principal loading axis is quite critical. And one of the key advent of our work was to ensure that the fiber or the yarns had zero twist. And then selecting preforms, we went along with unidirectional materials and multi-axials. We kept these to be non-crimped so that there was no third dimension misorientation, which could reduce the strength and stiffness by 5 to 10%. And we use resin transfer molding processes and an UV stable unsaturated polyester as the matrix. And we can see from our analysis that in terms of specific flexural modulus, the flax performed better than the e-glass composite, and even the back calculated fiber stiffness of flax was 75 gigapascals. So some of the details of the following case study on the biocomposite blade are in this paper, and you might also find it a bit more details of the design in this more recent paper. We did some analysis and load calculations based on the 61400 loading standards and determined the loads in fatigue conditions as well as for normal operational conditions. We fabricated the turbine blades. We found that the biocomposite blades were lighter. Fiber mass savings were 45%. And because of the flax blade being 10% lighter, the centrifugal loads would be lower as well, which is an advantage. We tested the blade as well. And you can see one of the blades being tested over here, which deflected quite substantially. Here's the tip displacement and a load application curve over here, significantly more than the e-glass blade. But nonetheless, based on our analysis and testing to the 61400 standard, the biocomposite blade survived both the normal operation load and the worst case load. However, the tip deflection was quite substantial. So something that we need to improve is the stiffness, the flexural rigidity of the blade, which was quite a surprise. That it's passed in terms of strength, but not necessarily in terms of stiffness. Something interesting also was the nonlinear response, which the standards do not consider based on synthetic materials that we typically use. We did some fatigue analysis, and it was quite apparent that fatigue was not a problem for these natural fiber composites, and we would quite easily surpass the 20-year design life in terms of fatigue. And in summary, plant fiber composites are they are promising lightweight structural reinforcements for load-bearing applications, and they can be replacements to conventional fiberglass although something to look into is to try and improve their flexural rigidity. And this could be to do with the design of the blade itself in terms of how the layering within the spar works, for example. But the properties are predictable without significant variation. Something else that we need to develop further is the development of low-cost reinforcements that are also low environmental impact, because our current analysis demonstrate that they are not always necessarily cheap and environmentally friendly. I'm happy to take any questions that you may have, or focus on elements that you may want me to.
Yes, thank you very much, Darshil. Very, very interesting. And I'm sure there might be some questions for you or comments. I will take them up now.
Yeah, Garrett Smith here. I've got a question. You know, are there bio-resins that you can use as the matrix to create your composites that are completely, you know, ecological then?
Yep. So there are no 100% bio-based resins. Well, that's wrong, actually. There is one 100% bio-based resin, which is called, which is from transfuran. It's a sugar-based hemicellulose-derived resin. It's conventionally used in the foundry industry. I have some of it over here, actually. So that can produce quite stiff materials. So this is a non-woven reinforcement with that. The problem with this resin is that it doesn't work with, because it fabricates through a polycondensation reaction. There is quite a lot of water inside it. So you need to try and evacuate that water. And therefore, what we have found is pre-pregging is one of the only ways to make it work. So it's possible, but also this resin is a bit more brittle than the wind energy sector typically uses, which can be epoxies that have failure strains of even up to 15%, whereas this resin has a failure strain of more around 5% or so. But it is possible. Other than that, there are a few bio-based epoxies, but the bio content tends to be 30 to 35%. I don't think it has surpassed that. But I think you're right that the resin sector is the one that needs development next. I think there are epoxidized soybean oils and things like that, but you still need to add styrene or something else to it to get the strength and stiffness high enough.
Okay, thanks.
Yes. Other comments or questions?
Yes, good afternoon, Alexander. Sir, I have a question about how do you think is the main barrier to deployment, like commercially, this project? Is the manufacturing or the primary material to have enough storage? Please comment about that.
Yeah, I think that's a great question. I think there are a couple of things. I think firstly, the challenge with the small wind turbine sector is that it incorporates quite discrete players, and therefore the supply chains can be a problem with some of these materials at least. So it depends where you're getting your fibers and reinforcements from. So that would be one of the challenges. In Europe, you can get quite a lot of these quite readily from France or Belgium or Romania, for instance. But the price is still significantly higher than that of fiberglass. And because small wind turbines are already, they can be expensive for, you do not want the blade to be any more expensive than they are, let's put it that way. And therefore, an alternative to e-glass that is cheaper is what is need to be developed. And perhaps we need to look into, for 1 kilowatt or 2 or 3 kilowatt machines, if we are using non-woven fibers, then we can meet the price point quite easily. And then it's the matter of trying to develop non-woven reinforcement products that are based on plant fibers. So I think that would be the next step. It's happening quite readily in the automotive sector, but I think what needs to happen, so this needs to transfer onto the small wind energy sector next.
Thank you.
Okay, thank you.
Yes, please. Okay. Are there further questions or comments? Well, if not right now, it might come a bit later. I think that now we will go into the discussion stage.